Hey everyone, we are here in the Corsair validation facilities. I'm joined by Bobby Kinstle. And Bobby, what do you do here? What do you know about this stuff?
So I'm the thermal engineer here at Corsair. I design all the cooling systems. That includes fans, liquid coolers, heat sinks. I consult airflow, anything that involves heat transfer or cooling.
And the first machine or setup I want to talk about is the thermal chamber. So in this room, which you'll see some of this in a moment, but there's a wind tunnel for fan testing, thermal chamber, there's a chroma setup for power supply testing. With this, let's just talk about the very basics of a thermal chamber. So we've already said why you would want one in previous content, but what are some of the different types of chambers available, like humidity, temperature control?
Right, okay, so basically a thermal chamber is a heater or a refrigerator in a highly insulated box. So you set the temperature that you want on here, and that can be a high temperature or a low temperature for whatever you're trying to test for, and then it maintains that temperature. And some of them are programmable so that they can go through different temperature ranges.
Right.
These are basic temperature-only chambers, but they also make humidity control chambers, some chambers with liquid nitrogen for extreme cooling. Some chambers have shock and vibration tables in them for extreme vibration, that sort of thing. Some have dry air injection so they can get to extremely low humidities or extreme temperature conditions. But for this industry, temperature only seems to do the job just fine.
So in what use case would you want humidity control for a thermal chamber?
If you were building products for a very highly humid environment like Southeast Asia, or you were concerned about corrosion or delamination of your circuit boards, for example, then you would definitely want a humidity chamber. We do that kind of testing, just not at this facility.
And we were talking just before shooting this video about humidity and how it impacts the heat capacity of the air. So let's run through that again for viewers.
Sure. The more humidity is in the air, the more heat the air can carry per unit of volume. And that's because the air density increases. So if you have a cubic foot of air at 20% humidity, you're going to be able to carry a little bit less heat than a cubic foot of air at 80% humidity. So in that regard, even though high humidity is very uncomfortable for us people, that actually helps the computer carry heat better.
Got it. And this chamber here, what are I guess you test your coolers cases in here, or how do you deploy the chamber?
Yeah, we put in these wire shelves that are up here on top. We can put a computer in here, or just a power supply, or just a cooler. I can show you in the next chamber over. We have a setup for testing processors. We use a thing called a thermal test vehicle, which is an actual processor made by Intel. And it goes into an actual processor socket and has the same mounting as a heatsink. You can attach a heatsink to it, and then the wires come out of this thing, goes to a power supply, and you turn it up, and it's a heater. It's just a heater chip. It doesn't actually compute.
Right.
And then I can say I want 100 watts, and then I can measure the temperature at the top of the die and its temperature differential, and then calculate how well the heatsink is working.
All right, so you can basically simulate a CPU. Because you can set the wattage, I guess, so you simulate the higher TDP or lower TDP chips.
Exactly.
Cool.
I can dial in whatever power level I want.
Right. So that's pretty cool. Okay, so we've moved camera shots. This is what we were just talking about. So
Correct.
Can you walk me through this?
All right, this is an Intel thermal test vehicle for Socket 2011 processor. It has a Socket 2011 sized CPU device here. Has a heater built into it. The heater is the same size as the microprocessor in real life, so it has the same heat flux per square millimeter as a real processor. This little line right here on top is a thermocouple that's embedded in there that allows me to measure the temperature at the very top of the package. I can measure the temperature of the heatsink, or I can measure the temperature of the ambient, and then calculate the effectiveness of the heatsink and its performance in degrees C per watt. I know how much power I put into it by running it with my DC power supply over here. So I know exactly how much power is going in, I know exactly how much heat's coming out, and then I can have a very good idea on the performance of the thermal system.
So for this programmable DC power supply, what can you tell me?
So as the name suggests, it's a DC power supply. I can set it to output any voltage that I want. It has current limits for safety. But what makes this very special isn't just that it's programmable, is that it has highly accurate metering built into it. So I can say, we've got 4 digits of precision on voltage and current. So I have a very, very good idea how much power is going into it. It cares so much that it actually measures the voltage at the TTV, not at the terminals here. So it compensates for the voltage drop through the wire.
Oh, cool. Okay, so now we are in front of the wind tunnel. Let's start with the report that you have on screen. What are we looking at here?
Okay, what we're looking at here is the actual wind tunnel report for the Corsair ML120 blue LED fan. These lines here, each line represents the pressure and flow at a particular point. So this axis is pressure, this axis is flow. The maximum pressure spec that you see on the box is always measured at 0 flow. The wind tunnel closes itself completely, runs the fan at a speed, measures the pressure at this location, and then plots that point here. This point is not useful to system designers other than to just have some way of comparing the system, because this doesn't occur in real life. If you have 0 flow, it's not doing any good for you at all. The wind tunnel begins by opening valves inside here and allowing some air to flow from the first chamber into the second chamber, and that reduces the static pressure and the flow increases. So as that happens, the next data point is here, and then it opens up some more, and here, and here, and here, and it works its way all the way down until the pressure here equals atmospheric pressure, and that is the 0 resistance point, or maximum flow, which is the other spec that you see on the box, which is also doesn't occur in reality, because if you don't have any resistance, there's nothing in the way of your fan.
Right.
Just, in reality, your system will be somewhere in between these points. And you can plot a resistance curve for, say, like a radiator, and that curve will go up in this direction. And where those two curves intersect is the actual pressure and flow that you will receive when you combine those elements in a system. That's actually the really useful information. So each one of these lines is a different speed. There's 100%, 90%, 80%, and so on, all the way down to 20%. The horizontal lines here are the fan's RPM. Excuse me. These are the fan's RPM, and so this blue line corresponds with this orange kind of peach colored line, this green line with this purple line, etc. It shows the RPMs over here. And as you can see, this fan is very stable regardless of the amount of resistance it receives. It doesn't really fluctuate in speed very much.
And so that's the report you get after using it. Mechanically, let's, I guess, walk from this end to that end.
Sure.
What's going on inside of the wind tunnel?
So let's back up just a smidge. Here is the plate where we mount the device to be tested, a fan or a radiator. I've even hooked up whole cases to this thing and measured flow resistance in cases. This ring right here is attached to 4 pressure taps. This is the static pressure sensor. It measures this in relationship to atmospheric pressure outside of the room. Inside here there are several screens. Those are to diffuse the flow so that the air flows at the same speed through the entire diameter of the wind tunnel. That's necessary for the calculations because the math makes certain assumptions about the diameter of the wind tunnel and how fast the air is flowing. These 2 pressure taps here are differential. They're measured against each other. This is the high side pressure. This is the low side pressure. In this plate here in the middle, there's a series of valves that start out about 1/2 inch in diameter and go all the way up to several inches in diameter. And it can open 1 or more valves depending on the type of test that it's doing. This chart here actually shows the smallest valve is 8 millimeters in diameter, and the largest is 42, but then it's 32 plus 42 and all. And it tells you the CFM range for whatever combination of valves you have open at that time. So when measuring the differential pressure across here and knowing the exact diameter of the valve, it knows the barometric pressure and it knows the temperature and humidity of the air, calculates the air density, can then calculate the exact CFM flowing through the system. This chamber has a couple more screens in it to equalize the flow, and then that tube goes out to a big fan right there. That's the counterblower. This is necessary because the wind tunnel itself has significant airflow resistance, and so it actually pulls a vacuum in this chamber in order to get the flow that it needs to achieve in the first chamber. This chamber often operates below atmospheric pressure. That's normal. So in order to get to this chamber, this point here, to equal atmospheric pressure, this chamber here has to be significantly below atmospheric pressure.
Very cool. Then wrapping it all back to the end product, this is the numbers that come up on the box at the end of the day, come up in the new specs sheet. Comes from something like this, I guess.
That's correct. All the published specifications for all of our fan products come out of this machine. This machine costs about $75,000, and once a year I fly a guy out from Taiwan to come calibrate it. His calibration reports are NIST traceable, and you can actually go up on the National Institute of Standards website and look it up. So I am very confident in the numbers and performance data that comes out of this machine.
Awesome. So for more information, as always, link in the description below. We'll have an article with more information. Thank you, Bobby, for joining me.
Certainly.
We'll see you all next time.